Hi everyone. Now let's wrap up today with adaptation paths for transformer architecture. Here's Narendra, CTO at Deep Kapha AI Labs, who will walk us through this process. Narendra, you can go on and show us your presentation.
Sure. So welcome everyone to Adaptation Paths for Transformer Architecture. I have shared the link for this Jupyter notebook along with everyone in the chat. So you are feel free to follow me while I run this notebook in an interactive way. And if you get stuck at any point, you are free to ask me as well. If you are going to join me while running this, then I would ask you that you switch the runtime to T4 GPU for it to actually work within the given time frame. So for some reason I am okay. Give me a second because my screen isn't being like scrollable or active. Okay, great. Now I can scroll. So sorry for the wait and welcome again to Adaptation Paths for Transformer Architecture. In this tutorial, we will go through the modern transformer architecture and see uh, what are the paths so that we can use. Excuse me, is there like a technical difficulty where like if I share my screen, then I cannot like access my own screen?
It should be working. Have you shared only a single screen?
Yes.
It should not have problem with that. Let's
Because I cannot scroll or like do enter or anything like that.
Could you maybe change the browser to Chrome? Do not use the Brave browser.
Okay,
We could try
it
that.
could be that. Yeah,
Yeah.
give me a second. Sorry for the wait. It's a bit weird. It's in the chat. I just sent it like a minute ago. Can you confirm that it's in the chat right now? It's a Google Drive link.
Yeah, it should be visible for all.
By using Google Chrome. Okay. So
Okay, it's working. We can see
yeah,
it
it's
now.
working. Yeah.
Yeah.
So sorry to waste your time, but welcome back to Adaptation Paths for Transformer Architecture. Over the last few years, we have seen that most of the models that we see deployed have converged to the transformer architecture because of its high expressivity. This expressivity comes from the fact that transformer architecture is an O(n) square architecture. That means that given a sequence, it attends to or it sees every single token to predict the next token. And this is why it has seen a large amount of success in being deployed. Another advantage of transformer architecture is that while training, it sees the entire sequence at a single time. While carrying out inference, it changes the token based on the entirety of the history. So this gives transformers an inherent advantage in sequence processing, but it also comes at a cost. Due to this high expressivity, their retraining and training is prohibitively expensive. So we need to find out ways to do this without spending the compute that is prohibitively expensive. And for this, I have created today's lecture, which is several adaptations paths that we can follow while keeping the compute costly. So in today's lecture, we will first go through the transformer foundations, and we will quickly revisit the core transformer block as well as the decoder only architecture and how it differs from the encoder decoder architecture that was presented in 2017 Attention is All You Need paper. We will then go into how to adapt these transformers using a lightweight adaptation method called LoRa, which is low rank adaptation matrix. And after we see how to use LoRa with Unsloth, we will go through several different methods which build on top of LoRa, but which are not yet famous and do not have community support, but they offer much more expressivity in adapting the transformer blocks. For this, I have shared a custom code, and the link to that is at the bottom of this Colab notebook, but we will go through that when time comes. And at the end, we will also go through our own variant that Deep Cafe Research has put forward called Adaptron, which combines all these adaptations paths into one robust path that anyone can follow. So let's dive into it. Before we jump into how to adapt a transformer, we need to understand what are the components of the modern transformer. And if you look at the diagram that Vaswani et al. Put forward, we see that they follow an encoder-decoder architecture as opposed to the modern decoder-only architecture. The encoder-decoder architecture allows people to process two sequences at a time, a sequence that acts as a context and another sequence that is the query, which gets generated token by token, depending on the context. This particular architecture was initially put forward for translation, and machine translation requires this because in most of the translation use cases, you need access to the entirety of the sequence in the host language before you can translate it into the target language. Whereas most of the real life use cases only depend on what the model has seen before. So we have seen a shift from encoder decoder to decoder only transformer. Another advantage of decoder only transformer is that it drastically simplifies the architecture flow. So as you can see in this encoder decoder block, we have two types of blocks. We have a stack of encoder blocks and a stack of decoder blocks. They're quite similar in their structure, but there are some fundamental differences. First is that you need to add positional embeddings at both the context, which is the input sequence, and also the output sequence, which is the one that you are currently generating. Underneath, they share a similar block in which you have a multi-head attention followed by addition and normalization, then a feed-forward neural network, and again addition and normalization. These residual connections allow the transformer to incrementally change its own representation. So you can think of it as you start from an input X and you create a different representation of that input through the attention mechanism, and you use that representation with the old representation together so that you can think of it as an incremental change. Then we repeat the same process through the feed-forward neural network. The multi-head attention or attention allows the sequence to, like different parts of the sequence, to determine what part of the sequence should, other part of sequence should change. Whereas the feed-forward neural network only focuses on point-wise. So what the value of token itself should change rather than what other tokens think its value should change. So it's kind of like scatter and gather mechanism in which you see the sequence and you learn from the other parts of sequence, and then you only focus on yourself and improve yourself. In the decoder block, you have another attention. So you have the traditional self-attention and you have a cross-attention. So instead of just focusing on what the tokens in your sequence say you should improve, you also focus on external context, which says, like, depending on these values, you should also change your representation. And then again, we have a feed-forward neutral. So as you can imagine that because it follows two different steps, encoding and decoding, it is kind of hard to train. Whereas if we remove the encoder, this only becomes like a pack of decoders, and thus the cross attention shall be removed as well, and it can follow a straight path rather than like a branching path. And this fundamentally makes it much more easier to run on GPUs or any kind of hardware accelerators in which the same computation can be repeated using different cores, such as TPUs. So we saw that it uses the multi-head self-attention, cross-attention, positional-wise feed-forward neural network, and residual connections. The decoder-only transformer drastically simplifies it. It has only self-attention, but in addition to being self-attention, it is a masked self-attention in which you only care about the tokens that come before you rather than all the tokens. So a token has only access to its history rather than the entire state. We keep the position-wise feed-forward neural network and we keep the residuals and layer norms. This is the architecture that most of the modern language models follow, such as Llama, Mistral, or GPT. However, the internals of the block have slightly changed. One of the primary changes that you see when going from the 2017 architecture to the modern architecture is that instead of the post norm, we apply a pre-norm. So even before going through the attention mechanism, you first normalize the sequence. And after the attention block is done and you have added the residual, you carry out normalization before feeding it into the feed-forward neural network. This has led to a higher training stability because if your inputs are normalized before you process them, then the magnitude of gradients is low. And if magnitude of gradients is low enough, then you can have training stability. So this is another change that the decoder-only transformer has seen from the encoder-only transformer. This design is simple and highly effective for generative tasks, and this is our focus today. However, people have because these blocks are easy to stack on, people have started to scale up more and more. For example, even the smallest usable model that people use in practice is approximately 1 billion parameters. And typically you get a better performance as you scale up. So it's not very rare to see more than 200 billion parameters at a time while scaling up. So let's take an example of how we would modify a 7 billion parameter model. To modify a 7 billion parameter model, we need a copy of its weight. So that is 7 billion parameters into the representation that you would want. So that is typically FP16 or floating point 16. And that means that you are holding 14 GB in memory just to hold weights. In addition, you need another set of equal weights, that is the change in weights. So that is another 14 GB. And you would need optimizer states, which are the optimizer parameters per parameter. So that is another 14 GB. So that means that to hold or to optimize a 14 billion 7 billion parameter model, you need more than 40 GB of memory. Now, if you are well versed with the modern GPUs, you know that even the A100s are limited at 80 GB. However, we aim to train and adapt much bigger models. So it is infeasible to use that kind of memory in practice. So we need something that is much more efficient. This memory wall prevents researchers especially rather than the industry, because industry can most of the times afford to buy or at least rent bigger GPUs. But this wall prohibits researchers from building on top of other people's work, which is something that we should avoid because we stand on shoulders of giants. And each step that we build helps not just us, but other people. So the solution to this is something called PEFT, or parameter efficient fine tuning. Instead of optimizing all the parameters, we come up with several strategies which select the parameters that we should optimize, and we restrict those to a lower number so that we can reduce the size of the 14 GB in memory, or like 40 GB in memory, to something much smaller. And we have found out that it is quite plausible to do so. And the reason for that is something called intrinsic rank hypothesis. So even though we use large matrices in practice to represent the model, the internal rank of those matrices is actually pretty low. That means that they can be represented using smaller matrices. It's just that finding those smaller matrices while training is a prohibitively hard task. So our problem is that we want the updated weights based on the current weights, based on some learning rate, and based on a gradient of loss that is a function of these weights. Now, since this gradient of loss is function of the weights, we have some trouble because we are replicating the same size as the weights. So our job in parameter efficient fine tuning is to replace this gradient of loss with a function of something else other than the weights so that it can fit in our GPU. The first method that we shall discuss today is called LoRa, or low rank adaptation matrix, and we will go through its essence as well as some maths. The LoRa approach overcomes this low rank representation by factoring the matrix into two smaller matrices. So imagine that you have a giant weight matrix W, which includes the query, key, and the value projections. LoRa freezes the initial matrix, which is the W matrix, and it adds a smaller side path, which divides the W matrix into two different chunks. These chunks, when multiplied, give you the same size as the W matrix. So for example, if you have a 4096 by 4096 matrix, which is approximately 16 million in size, you can denote it as 4096 into a rank 8 matrix. So 4096 into 8 multiplied by 8 into 4096. So this is rank 8, which is much lower than the whole rank, which is 4096. But you get the similar representation when you multiply these two matrices together. That is 4096 by 4096. But you will observe that the number of parameters that are required to represent A and B is far smaller than the multiplication. So it is 16 times 4096 rather than 4096 by 4096. So this represents a massive reduction in training parameters. So we rewrite the update equation as follows. We still want to achieve the same output, and we want to have our frozen pre-trained weights multiplied by X, but our low rank update is denoted by B into A, which are trainable matrices of lower ranks, into the input. So let's go over again why this is efficient. First is because instead of computing the gradients through the forward path, we are only computing them through a parallel and much smaller path. We are using a scaling mechanism so that over here, instead of BAX, we are using alpha BAX, which allows us to determine what exact amount should be added to the main input. Think of it as another learning rate on top of a learning rate. And we initialize one of the matrices, either B or A, typically B, as a zero matrix. That means when the training starts, B into A due to B or A being zero is zero. So at the training start, you get the exact same behavior as the model would get if there was no LoRa matrices added to the plane. Another advantage of LoRa is that it has mergeability. And that means that there is zero latency after you train. Once you train a LoRa matrix, you can simply consider that as delta W and add it to the original weights because they are of the same size. So you can multiply the B by A and add it to W. And then you have a new pre-trained model, which is of exact same size. You have not added any new layers to it. And so your forward pass will have the exact same timing as the original model. This gives LoRa a high amount of credibility because even though you are changing or adapting the model, you are not adding any extra letters. The popular library to code LoRa's is Unsloth. And we will go into what is Unsloth and how to use LoRa's in the following section. If you are running this notebook from home, I would invite you to run this along with me. The first cell should take a few seconds because it installs Unsloth since Colab does not support it, and it also installs all the allied libraries that are needed. So it should take approximately a minute. We can go through what Unsloth is till it runs. So as we saw that we compute the forward pass and the backward pass, these involve several operations. PyTorch typically creates a dynamic graph under the hood so that it carries out the backward computation or forward computation for each of those operations. This means that more the number of operations, slower your forward pass and backward pass will be. The way to overcome that is something called operation fusion, in which instead of saying that we want to compute the forward pass for operation 1, operation 2, and operation 3, we will combine these into one and just carry out one operation. So this is called operator fusing, and this is what people do to make things faster using several libraries. If you use CUDA, then you can write raw CUDA kernels. However, that is something that requires a high amount of expertise and also leads to brittle code because then you are tied to a single architecture. So OpenAI has came up with a library called Triton, which allows you to write kernels using a simplified Python dialect. And once you have that, you can optimize the said kernels for any GPU that you have, depending on the memory availability. And once you optimize these kernels using their fine-tuning process, you are able to run your workloads at much faster rate. Now, fortunately, Unsloth has taken care of writing these kernels for LoRa operations for most of the popular models. So Unsloth currently supports four to five different architectures, including Llama, Qwen, Mistral, GPT, and several audio and video architectures, which are based on these. So it has written the kernels required to do the LoRa updates faster for us. And so that's why we use it. Another advantage of Unsloth is that it ties into the popular Hugging Face ecosystem. So we have access to all the models which are on Hugging Face Hub, and it runs faster on our GPU. Okay. So to start with, we will load Unsloth. And let's go through what we are going to do during this script execution. First, we will load a model into a 4-bit format, and then we will attach the LoRa configuration of what the rank we want and what is the alpha we want, etc., to this architecture. And we will create the LoRa matrices and fuse them or add them as a wrapper on top of the existing model. And we'll set up gradient checkpointing, which is something that we do for efficiency. So while computing the forward passes and backward passes, we will save the state to the disk, and so that we can have faster lookups when computing the next backward pass. And then we will take two instruction datasets, one for reasoning and one for not reasoning, just conversational. And we'll fuse them together and train a LoRa on top. We will go for a small model, which is Qwen 3.6 billion parameter model, and we will fine tune it to have better performance on both reasoning as well as conversational abilities. So while Unsloth allows for any arbitrary sequence length, we will go for 2048, which seems enough, which is approximately 1 page worth of content. The D type of this system is going to be auto, because Unsloth is clever enough that depending on the GPU that you have access to, it chooses the best data type. So if you have access to something such as A100 or H100, then it will go for FP8 because it has FP8 cores, whereas otherwise it will try to do most of the computations in FP16. The model that we load, however, will be in 4-bit. So instead of the normal Qwen model, we will go for one that is created by Unsloth and converted into 4-bit format. This would take like a few seconds as we need to download approximately 1 GB of data. And as you can see, even the smallest model, which is 0.6 billion parameter model, requires you to download approximately half a GB worth of data, even though it's quantized. So if it was not quantized, then the same model would be like at FP32, which is the full precision, somewhere around 2 GB. And if you look at the GPU that you guys have on your normal laptops, they're capped at 1 to 2 GB. If you have like a dedicated NVIDIA card, then it can go around somewhere between 8 on consumer hardware. Whereas, of course, if you go for enterprise hardware, then it's somewhere around 80. But even then, the smallest model requires such a size to store. And this is why parameter efficient fine tuning is important. So next, we choose several hyperparameters that will allow us to set the expressivity of the adapter that we are learning, which is the LoRa adapter. The first one is rank. We typically choose rank which is divisible by power of 2 or 8. The reason for this is because most of the architectures are created in such a way that most of their hyperparameters are divisible by power of 2 so that they can be efficiently accelerated on CUDA hardware or like NVIDIA hardware. The reason for that is because if something is divisible by a power of 2, then it gets executed as one block. Otherwise, you need one extra block that is not divisible by power of 2, ran separately. And this separate block typically leads to a tremendous amount of slowdown. So most models follow the power of 2 rule. And so we need to follow the same rule while creating the LoRa adapter. Typical values range from somewhere between 4, 8, 16, 32, and maximum 128. The reason for this is because most of the LLMs typically have a size of hidden size of 512 to 2048. If you want to save on the parameters, you need to have a rank that is lower than this. If you have a much higher rank, then the performance comes close to full fine tuning. So it is far more accurate, but at the same time, it is far more resource consuming. So over here, we will choose a value of 16 or 32. If you have a model that is trained on a tremendous amount of data rather than like a medium amount of data, then you would not want the model's behavior to change a lot. And in those scenarios, you want the rank to be lower, such as 4 and 8. We use the scaling factor the same size as the rank or the square of the size. So over here, we are going to set it as 16. Then we need to give unslot the target models. This requires some understanding of the underlying model. However, most of the models that are available on Hugging Face follow a standardized way of naming things. So it makes things a little bit easier for us. We'll go into like a example model later on and see the intricacies of it. But for now, we will consider that we are going to optimize the attention as well as feed forwardiness. For attention, you need the Q matrix, the V matrix, and the K matrix. For the feed forward neural network, you need up projection and down projection. So these are your target models or the name of the modules within the model that you want to target. We have LoRa dropout as 0. If you have a high amount of data and you don't want the LoRa to be overfit on it, especially if the size of your LoRa matrix is quite high due to rank being high, then you would apply LoRa dropout. However, in our case, we are training on a limited amount of data, so we won't apply LoRa dropout at all. And also, if you don't apply LoRa dropout, then Onslaught has faster kernels. So I would suggest that even at risk, when you have the high amount of data, you should go for zero dropout. And using gradient checkpointing allows the model to save on some memory by not holding the pieces in memory, but writing them to disk and then loading them as needed. So this is a strategy that Unslot has created, and this is usually set to either true or unslot. So let's create a wrapper model based on the original model. And since it will be initiated with 0 value, the performance will be exactly the same as the original model before we jump into the fine tuning. So now we have created or patched 28 QKV layers, 28 output layers. So we saw that the first the first 4 apply to the attention layers and the next 3 apply to the MLP layers. You can set a random state over here so that you will have reproducible results always. Next, let's go to jump into the data sets that we will use. We will use 2 data sets. The first is the reasoning data set called Open Math Reasoning. This contains the problems from Math Olympiad. So Math Olympiad is a competition that most of you will be familiar with, and it includes challenging problems in maths, and you need to have a robust reasoning. So these reasoning traces were created by another model called DeepSeek, and the problem solutions were given by the committee that organizes the Math Olympiads. The second is not reasoning dataset, it is just like a conversational dataset. So we'll load these datasets. And this is another nice thing that Unslot provides us, that it allows us to load any Hugging Face datasets. So you can change this later on at your own convenience or own use cases. And there are thousands of datasets available on Hugging Face, so you can train any of them with the given notebook. So let's see what is in the reasoning dataset. So we have an expected answer, a problem type, a problem source, the generation model for the reasoning traces, which is typically DeepSeek, the pass rate, the problem, the generated solution, and inference mode. And you can see that we have approximately 19,000 examples in the reasoning dataset. Let's go through the non-reasoning dataset, which is far more it's far more larger. And we have the conversations. So this is a example function that brings them into a predefined format. So typically for instruction tuned models or chat tuned models, you will find that they follow a conversational pattern in which you have a user asking a question and then assistant answering. This is done through something called Share GPT or Chat ML templates. So they try to bring datasets into a standardized form so that you can still use it the way you can use ChatGPT. We will convert the reasoning conversations into this Share GPT or Chat ML format and look at how it will look. So you have some special tokens that you are starting the assistant, you are starting the messaging turn, and the user says, "This is my problem." And once it ends, you have like a special token. Then the assistant's turn starts and you have special tags that denote thinking. Once the assistant is done thinking, you have the answer. We will also apply a similar format to the conversations, which are already pretty standardized, and see what we get further. This should take like approximately a minute for most of the people. You'll see that it follows the same structure, but there is no thinking over here. The thinking tags are empty. So you start the thinking token, you have some empty lines, and you end the thinking and you directly jump to answers. So having these two data sets allow us to go for both reasoning and non-reasoning. When you don't go for a reasoning model, then your inference is faster because you're not wasting time thinking, you're directly jumping to answers. Whereas in the first case, you are thinking and taking times, so you can solve harder problems, such as mathematics. So because there is a discrepancy in the sizes of these data sets, the reasoning data set is far smaller than the conversational one, we need to bring them to somewhat similar percentage. So we'll set to only use 25% of the non-reasoning conversations. Once we do that, we'll combine them into one. And as you can see that we took approximately 25% of them. So we have 19,000 reasoning and 25% of that from the non-reasoning. So that is 6,417. And we combine them together into one data set. So this is where most of your efforts in LoRa will be. You need to create data sets which are valuable. And you can either scrape them or use Hugging Face datasets, or if your company has a dataset, then you can use the share GPT functions that are shown to bring them into a common format. But this is where most of the time that you will spend will be, because the rest of the stuff is pretty mechanical. So now that we have the wrapper model, which has the LoRa matrices, we create a training instance. The training instance takes the model, the tokenizer, and some extra parameters. So over here, we'll train for 50 steps, but you can also train for like one epoch. So on T4, it takes somewhere around 4 hours to do a parameter efficient training. Whereas if it's just 50 steps, then it will be done in somewhere around 5 minutes. But even in just 50 steps, you can see a significant difference in the model's behavior. You typically do not expect sub 1 billion parameter models to give you appropriate answers, especially that when you require a high amount of reason. But this will allow us to achieve that. So first, it will tokenize the entire data set that we have, and this will take somewhere around 2 minutes. You can also increase the dataset number of processes to tokenize to more than 2. But because we are restricted by the environment and I want everyone to be able to run this without taking a Colab subscription, I have kept it 2. If you have a Colab subscription, or if you are using a high RAM machine, then you can set it to 6 or even remove it so that it can be automatically found out, the optimum number. And once you run this, you will have a tokenized dataset and a trainer object ready to train. Once you have that, it's just a single call to train and your model will begin training. So we still have to wait like 35 seconds. We'll see the GPU stats like over here. And if you are on Colab and doing this with me, okay, I cannot use my mouse, but I can use my keyboard. That's good to know. You can click on the RAM and disk icons so that you see how much is your GPU memory currently being consumed. It should be somewhere below 1 GB because we have only loaded the model in memory so far. So you can see that we are on Tesla T4 GPU and our max memory is somewhere around 14 GB. We are only using 0.709 GB, so even less than 1 GB of memory, even though the same model would have caused us to like use approximately 5 GB of memory, 2 GB for loading the model in higher precision, and more 2.5 to 3 more GBs for the optimizer states if we were not using the parameter efficient way. But now we are sub 1 GB. The reason is we are using a lower precision for the model itself, and we are using parameter efficient methods. Since now we are done with this, we can simply call the train object and it will begin training. And within 5 minutes, we will have a model which is able to both reason and solve complex problems as well as give the thinking traces. So you can see that it has begun training and it will like finish somewhere around 5 minutes and the loss will steadily go down. even at the start, the loss is somewhere around 0.76, which is a good starting point because we start with a pre-trained model. But as it goes along, the loss will go like further down. Some fluctuations are expected because of the randomness inherent in the system. But since we have set the random seed, we will get the same results even if you run this notebook another time. So you can see that we are actually going down in loss compared to the starting point. And the reason for that is because it's training those small number of parameters. And you can see that even though we have approximately 600 or like 700 million parameters, we are only training 1.67% of them. So we are only training 10 million parameters out of 600 available parameters. This should take like a couple more minutes. I welcome any questions you may have during this time. Okay, since there are no questions, we can jump back to. So we are close to finishing off the training, and we can see that we are far lower in loss compared to the starting point. I think we need to wait for like a minute more. Once you have successfully trained the said model, you can either save it to the disk or merge it for like offline serving. We usually merge it into FP16 so that it can be used by different inference frameworks such as VLLM or Ulama, or you can push the said model or just the LoRa weights to hub, whichever might be preferable to you. You can also perform like a benchmark based on like a headout set, or you can conduct like a chat test, which is what we are going to do. So we are at 43 and I think, yeah, we are done. So within 4 minutes and 69 seconds, like 4.69 minutes, we trained on a small set or subset of the reasoning and non-reasoning data sets. And we used only 3 GB of memory to achieve this. So even on the consumer level cards, this is possible. Now, because the resultant model is 0.6 billion parameter model, you can even use it on web without any CUDA acceleration. Let's test it out. So we'll use a streaming inference and we'll ask it to solve a mathematical question. First, without any thinking, so that we can see if it can directly jump to answers. And we can see that it directly gives us the answer without any extra thinking steps, and the answer is correct. You can ask the same question again, this time with thinking and with more available tokens. And you will see the model's behavior is different. So first, it thinks how to solve the problem, internally creates a scratchpad and denotes all the steps, checks it, and then provides the final answer. So we have instead two different behaviors based on the two different data sets that we have. So this will take a few seconds more and we will be done with it. And over here, we have the correct answer as well. In addition, it uses verification. We got the correct answer for both, using both thinking as well as non-thinking methodology. Now you can simply save the model by calling the save pre-trained method to save the LoRa version of it. Or you can call save pre-trained merged to merge those LoRa weights back into the original weight matrix to get a model that is exact same size as the original model is, and you can use it for further use. You can also save a GGUF, which is a version of file that is used by both OLAMA as well as Llama CPP using this. We'll just use the Hugging Face saving because that's the easiest and takes the least time. So as you can see that we started with 4-bit weights, but we are merging them to 16-bit. So now the size of our model increased from like somewhere around 600 MB to 1.19 GB. Next, we will jump into like some other variants of LoRa and what more there is. To do so, we won't follow the same methodology because unfortunately these methods are experimental, and for them there are no efficient kernels written by Unsloth. So if your job requires you to just fine-tune models, then I would say that you should opt for the LoRa methodology presented so far. However, if your job is to come up with something innovative, and if you are familiar enough to write your own CUDA kernels to make it fast enough, then you should go for other LoRa variants because they allow you to have more expressivity in the adapters. So let's go into some versions. So if you can see, why aren't they demoed the same way? If you click on it, you will go to a file on the Unsloth repository where it is explained how to make LoRa faster through custom kernels. If you are okay with waiting a bit longer and you don't mind the significant slowdown that comes with using manual kernels rather than handwritten kernels, then you can click the second link and it will take you to a library called PEFT by Hugging Face as well. It allows you to experiment with different types of parameter efficient fine-tuning methodologies, and including all the methodologies that we currently have. Unfortunately, PEFT is not a well-maintained library, and so some of the methods work only on a singular series of models, and you would need to find out which by going through the source code, which is something that I wanted to avoid because we cannot show a common use case for most of the methods. So that is why I have like used it as a link. However, if you are interested in implementing all these methods yourself, I have created a GitHub repository in which I provide an implementation of the modern transformer block that you can use to load almost any kind of pre-trained model, and several different methods of adapting them. So we'll git clone it. I think I may have already done it. So it's already exists. So we have it. We'll go through it later. So we will go through some LoRa variants before we jump into the other methods. First is QLoRa. In fact, if you might not have noticed, but we have inadvertently used QLoRa because in QLoRa, you start with a model that is quantized, but you don't apply quantization to the LoRa matrices. We started with a version of Quen, which was 4-bit quantized, but we did not apply the quantization to the adapter matrices. So we inadvertently trained with QLoRa, even though we did not specify it. So QLoRa doesn't need any specific implementation beyond what exists. The second methodology is called DORA, which is weight decomposed low rank adaptation, in which instead of two matrices B and A, you have a magnitude and a direction. You compute the magnitude and direction from the B and A matrix and add another parameter on top, which is adaptive magnitude, and it will work better because it is more physically grounded. It also requires you to add some more parameters in addition to the LoRa parameters. So typically, the size of a DORA matrix is higher than the LoRa matrix. Then you have VERA methodology, which is vector-based random matrix adaptation, in which instead of training both A and B, you freeze them to some random values and only train a smaller vector in between A and B so that that vector gets trained, which is R into R, and the projection remains the same size. So it reduces the trainable parameters even further than LoRa. However, there is some debate on whether such a drastic reduction on trainable parameters, which is, and LoRa already reduces the number of parameters by 10x or like even 100x, because we saw it was like only 1%. So 0.01%. Is it enough to train transformers? There is some debate on that, but it could be a useful methodology. There are some other alternatives rather than LoRa that we can use as well, because LoRa worked on something called the reparameterization trick. In reparameterization trick, you denote the weights in terms of other weights, but they have the same shape. Whereas you have other methods that add the new parameters directly to the pre-trained model. Some examples of that are adapters. Adapters add new parameters completely separate from the trainable parameters of the frozen matrix. This leads to ease of training because you don't have to think about how to merge them. They just exist separately from the model's parameters. However, they add a little bit of inference latency because you are adding more computation to the phone. The second way of improving transformers is something called prompt tuning, in which you define by text some number of tokens that should always be appended before you process your sequence. So for example, if I wanted to create a model which always answers in Italian, I would add an instruction always answer in Italian in words, convert it into tokens, and prefix them to the model. So while computing the generation, it uses these same tokens before it sees other tokens. So you will get a model that will always answer in Italian. Now, you can use it even without training. You can just use your tokenizer and append this every single time. Or you can start with some textual representation, like always answer in Italian, and you can collect a small data set and you can mark these tokens, which are embedding vectors, as trainable. This is typically approximately 5 times more than LoRa, but it leads to better performance. And it's pretty easy to train. Next, we'll see what is Adaptron. Adaptation is our approach based on unifying these three different methodologies. We take some good ideas from everything that has existed before us. The first good idea that we saw was use of cross attention. We saw that in original encoder-decoder architecture, we used external context through cross attention. Now, this was something that we wanted to avoid while training the base model. However, once the base model has already been trained, you can introduce it without any significant lag in training time, because most of the training has already been done. So you can reintroduce the cross attention. So you can have additional sources of information such as those through RAG or any other methodology that you can think of where you have external context. RAG just allows you to bring relevant information quite easily using neural embeddings. If you have multiple different documents or chunks that the RAG brings, you can use cross attention again over them to make them into a fixed size vector, or what we call a scratch pad. So we divide it into two. First is RAG, which brings the vectors, like several vectors into the fold. It can be 3, it can be 8, depend, or whatever is your max number of retrieved vectors. And then you project them into a fixed size scratch pad using cross attention. Once you have that, you carry out cross attention between the scratch pad and your self attention. So that means that you are considering the context, the fixed size context, into improving your representations. You can also have something called cross attention over learned parameters. So we saw earlier that we have 3 different matrices, Q, K, and V. And these matrices come from X, which is the sequence that you are currently processing. However, we can make the Q and the V, K and the V fixed vectors which are learnable rather than coming from the input. This allows us to reason or learn over parameter tokens. So we treat the parameters of the model as another set of tokens in addition to the original sequence. And again, we see what has worked before us. So we use the zero initialization for stability. So like LoRa, where the B matrix is initialized to 0, we also initialize all of these components to 0. So at start, they have no effect. But as you progress, they have a significant amount of effect. So all adaptation is done through cross attention. The GitHub repository that I have provided you access to consists of all these methods and the host model itself. So how to go about choosing which methodology to follow? We have already kind of answered it, but if you are constrained by VRAM, then you should go for the QLoRa or LoRa methodology. Whereas if you have a challenging task where lower representations don't work and you don't have memory to compute or go for full fine tuning, then you should go for Adaptation. And since I already said this before, that most of this notebook is pretty automatable besides the data collection part, because you choose the same amount of R or training hyperparameters every single time. So you can write it in a cron job or any automation system and run the retraining repeatedly if you have the hardware, which is exactly what we do at Lucid. It is our HTech startup, and we train continuously on different domains. So when the user wants to learn, let's say something about MLOps, and we have enough MLOps material, we create a separate data set, which is for MLOps, and retrain our model so that it can answer the MLOps related queries better. We also develop personalized models. So every so often, for all paying customers, we retrain the model so that they can answer their asking patterns better. And you can do so magically by just wrapping this given notebook into a cron job. So we saw what are transformers. We saw what is LoRa and how to train it using LoRa, and we discussed some advanced models. We have approximately 10 minutes for questions, so we can go for questions. And if there are not any, then we can go for like a review of the Git repository and how to use it. So I open the floor to any questions that you guys may have.
So if nobody has any questions, we can wrap up here. So thank you, Narendra, for a powerful close for today's track. And that's all for the stream too. Thank you for being with us today. We hope you learned a lot. Take care and enjoy the rest of your day.
Thank you, guys.
Bye.